Just to make sure you're in the right class, this is PG 323M, Reservoir Engineering 3. Should have all had Reservoir Engineering 2, also known as Reservoir Simulation. So this is the class where we get to put to use what you learned in Reservoir Engineering 1 and 2. I know in those two classes you also learn a lot of simple engineering models that you can sort of solve in closed form. In this class we're going to be dealing primarily with partial differential equations that are nonlinear and you can't solve in closed form. So we have to resort to a computer to solve them. We're going to write some of our own code, actually a lot of our own code, and we'll also use a commercial reservoir simulator, CMG. And what you'll learn is that you can actually write your own code in a few hours that can produce the same results as CMG, which is a very, very expensive commercial code. I think it costs like $10,000 a month or something for a service fee for that code. So who did some reservoir engineering last summer or maybe in previous summers as an intern? So what simulator did you use?
We used Smart.
Okay. What about you? You raised your hand? What simulator did you use? Do you remember? Oh, okay. What about you? IPA. Yeah. So the sort of two big commercial ones are CMG and Eclipse. CMG and Eclipse is Schlumberger's, right? But basically all of the super major companies have their own in-house simulators that they don't share. There's also several academic versions, and we'll talk a little bit about those. But basically, just as an overview, as a reservoir engineer, your primary job is sort of to figure out how much oil and gas you can produce in a reservoir. So somebody who works in formation evaluation will give you a picture of a reservoir and some information about the porosity and permeability and other things, and you'll have to construct a mathematical model of that reservoir, a numerical model of that reservoir, and then try to use what you know about math and physics to determine how much oil and gas is in the reservoir and, well, more specifically, how much can we produce from the reservoir given the conditions that we know. And then once we sort of decide that it may be economical, or part of the decision that it may be economical to go out and bring a reservoir into production, then our job as reservoir engineers to figure out how to do that and optimally, right? How do we get it out essentially as fast and as cheaply as possible, right? And so we can use reservoir simulators to help us with those tasks. And so part of the process of reservoir simulation is to understand the flow and transport equations. Essentially, that's what you should already know, and we're going to sort of review that. But that's Reservoir 1 and 2, sort of learn the fundamental equations. And then we're going to develop mathematical models. That's sort of one and the same as the first part that describe the physics. And then those mathematical models will be coupled nonlinear partial differential equations. So who's had a course in partial differential equations? Probably no one, right? I never actually had one until I was in graduate school either. But it turns out that it's not really that useful to take a course in partial differential equations because there's only about 5 in the entire world that can actually be solved with a piece of paper. It's very useful to take numerical courses like this one in finite elements and other things. But as an engineer, most of the problems we go out in the real world, they aren't nice closed form things. We have to make decisions about them. We have to resort to using the computer to solve them. And that's sort of the last point, that most of these PDEs can't be solved analytically. So it's going to make me do this every time. So along those kind of two big questions or big picture jobs as a reservoir engineer, how much oil and gas can we produce and how fast can we get it out, how economically we can get it produced, they bring rise to several other little questions, and really most of them relate back to economics. And the nice thing about, I heard Dr. Bauhoff say this morning that the reservoir simulator is a crystal ball. Well, I'm not going to go so far as to call it a crystal ball because at least the crystal balls I've seen in movies are always right. The simulator can be very wrong, but not because the computer makes a mistake in computing the answer, but because either there's not enough physics in the model, or as modelers, as setting up the problem, we made some incorrect choices, or we made incorrect assumptions about the inputs or about the outputs, right? So it's usually human error associated with it. But if we use that as a tool that can give us insight, then we can then do things like conduct parametric studies. For example, we can say, what if? We can say, we have a reservoir here, it's already producing X amount. What if we put an injector right here? Does that help us? And will it be worth the cost of actually putting the injector in? Right? So these are the type of questions that we can answer with a simulator, along with several of these other ones. So this is sort of the schematic picture of modeling and simulation. Right? We start with an engineering problem. We need to solve, in this case, our engineering problem is how much oil and gas can we produce, right, out of a given reservoir, and how fast can we do it? That's our engineering problem. And really, what separates engineers from physicists and everyone else is really this first step in the process, turning that engineering problem into a mathematical problem. So an engineer's job is to decide what physics are important and include those physics in a mathematical model. Right? A physicist's job is to include everything, right? Where every atom is at all time. That's what they want to know, right? But an engineer's job is to say, what were the most important physics, and everything else that we can get away with, let's throw it out so that we can get a solution in a reasonable amount of time under reasonable assumptions. And then with that, we have a mathematical model. Now, anybody really with a training in mathematics, physics, can do this second part, turn the mathematical problem into the numerical solution. And so that's going to be a big part of this class. You'll learn one of the techniques to doing that. There are many, many ways to take continuous partial differential equations and turn them into a discrete set of algebraic equations that we can solve on a computer. We'll talk a little bit about how we're going to do it in this course today. But this primary concern of this course is this bottom section, learning how to turn the mathematical problem into the numerical solution. And then once we have a numerical solution, the rest is we have to use our engineering intuition and economics to take that numerical solution and make engineering decisions, decide, should we put that injector in or not? So, these are the steps, I guess. I kind of covered these. We take the mathematical model and we construct that mathematical model because we have some understanding of the physics, right? We know how rocks and fluid behave because of observations from experiments, or possibly because we did even higher resolution numerical simulations. Sometimes what we infer or what we know about how fluid flows in reservoirs because we did simulations of, say, pore scale flow, right? And then we take the results from those simulations and we use them in larger scale. But most of what we know or use, is tied to experiments or observations in some way, and then we describe those with the conservation equations, mass, momentum, energy. I mean, that's really it. All of engineering can be, just brought back to conservation of mass, momentum, and energy, really. In this class, of primary concern will be conservation of mass. That's mostly what we're going to deal with. But really, if you want to have really, really accurate simulations, you also need to include, possibly conservation of energy and momentum and, chemistry and all kind of other effects, right? But in this class, we'll primarily deal with just conservation of mass. And then, the last two things there, I just sort of repeated what I already talked about on the previous slide. So the general idea, or the sort of numerical technique we're going to use in this class, is we're going to take our complex reservoir, right? And that reservoir has got very heterogeneous, structure in terms of the material properties. So porosity is changing, permeability is changing, all over the reservoir, right? And we're going to take that reservoir and we're going to break it up into little pieces, as smaller pieces as we can get by with. Now, what's that mean? Our simulation is going to be more accurate if we can get smaller and smaller pieces, but it's also going to cost longer. cost meaning computational time, right? So the more accurate, the smaller the pieces we break it into, the more accurate our simulation will be, yet the more expensive it'll be. And so we have to, as engineers, make those decisions, what's accurate enough. Or sometimes we do things called convergence studies, where we basically progressively use smaller and smaller grids, and we look at how the answer is changing, and then at some point we determine, well, this is good enough for our solution. And so, the picture there kind of describes it. We take this thing that has very continuous graded properties. So that the image on the left is actually a reservoir simulation where there's an injector and producer on each side, and inside those colored bands represent changes in permeability. So like red, there's one scale. So red and blue, like red would be high, blue would be low. Right? So changes in permeability throughout the reservoir, and we break that thing up into little discrete blocks. And inside every one of those blocks, we're going to assume that the permeability is constant, right? And so this procedure is called essentially finite differencing. You might remember this from a numerical methods class you took. You probably certainly have done it in one dimension. Here we're going to do it in three, right? But we're going to break that up into blocks, and each of these blocks have a constant material properties in terms of permeability, porosity, and when we get into multi-phase, saturation, other things, right? So we're going to be solving for pressure and saturation in each of those blocks. And now, in reality, reservoirs are very large, kilometers by kilometers. So these blocks, they're going to turn out to be as large as this room, right? In physical dimensions. And of course, if you go out in a reservoir, there's no single homogeneous piece of rock anywhere in the world that is as large as this room and completely homogeneous, right? So that's an assumption we're making right there. Almost all commercial reservoir simulators are going to use this sort of finite differencing or finite volume techniques, where they're going to be, basically each block has constant material properties. But I will just say, and we won't discuss it again, but I will just say that, when I first said all those field equations, there's multiple ways to discretize them. There are more advanced techniques for discretizing this, such that in each of those blocks you don't just have constant properties. You could actually introduce interpolation into the formulation. And so then across a block you might assume that the pressure or saturation varies linearly or quadratically. And so that's a concept that really comes from finite element analysis. But of course, the more complexity you add to the simulator, the more expensive it is, the longer it takes to get a solution. So really, these finite differences are about as simple as we can get, but they're also as fast as we can get. And that's why they're used in almost all kind of commercial simulators. So basically, we break it up, and then now we have discrete things. So we started with some continuous equation, differential equation. But when we introduce the discrete nature, we break it up into these little blocks, those differential equations become algebraic equations, right? And then we can just solve those algebraic equations like you've always solved. They're essentially just matrix equations. It's just, in this class, we're going to learn exactly how to construct those matrix equations. So again, of primary concern in this class is conservation of mass. So really, if we take every block in isolation, and we just write down the conservation of mass, how much mass goes in minus the mass that goes out has to equal the mass that's accumulated, right? And accumulation can come from compressibility in the fluid or the rock, right? And in steady state, then there would be no accumulation, and it's just the mass that goes in has to equal the mass that comes out, right? And so we take each of those blocks in isolation, and we write that equation. It's pretty easy, actually, when you write it, algebraically like this. Mass goes out equals mass that come in, right? At least in steady state. Of course, we have to do that for every component, right? And so in a real reservoir, there's many components, many phases, right? So there's oil and water and different, gas, all these different little species that could be in each block, right? In this class, we'll primarily just deal with like two-phase, oil and gas, and then we do this for every cell. So every cell, and then there's continuity across. So anything that's exiting one block has to be entering the one next to it, right? So there's a continuity across there, and that's what couples equations or ties them together, okay? And then we can construct a big algebraic matrix equations, and then we use a computer to solve them. Right? And so we'll review these in more detail in the upcoming, but there's basically the mass balance of the partial differential equation. It's a partial differential equation because there's derivatives in space. In this case, it's just one dimension, so x is a direction. So there's a spatial dimension x, and then there's also time. Right? That's why it's a partial differential equation. And in this case, we're solving for it's a two-phase, so oil and water, and we would solve these equations for the pressure and saturation. So we'd basically discretize this equation, solve it on every block, couple them all together, right? And when you do couple them, you get a set of a matrix equations. And while the matrix equations could be big, they're big because basically there's one row in the equation, one row in one column for every unknown, right? And every block has at least two unknowns, pressure and saturation, right? So there's one equation, one row, one column for every unknown. And if you have 1 million blocks, which is not unusual, I heard Dr. Baloff say this morning that Saudi Aramco has a model that has a billion cells, 1 billion grid blocks, okay? And so if you have 1 billion grid blocks, you have like 2 billion equations at least, in sort of the simplest model that you could come up with. And so now, while that's a lot of equations, it turns out that the matrix is really sparse. So they're always going to have some kind of structure like this. In one dimension, they'll always be tridiagonal. In two dimensions, they'll be pentadiagonal. So they'll have another off diagonal row here. But everything else is zeros. Okay, everything else is zero. So in a real commercial simulator, and we won't be so judicious in our coding in this class to worry about it, but in a real simulator, you would use very smart data structures such that you don't have to store all those zeros, right? You just store the non-zero values. So because storage in a computer also expensive, especially if you get really big. All right. So this is sort of what we're going to focus on, at least in the first part of the class, is how do we take those PDEs and convert them into algebraic equations. So what do you need to create a simulator? I mean, that's essentially what we're going to do in this class. We're going to create our own reservoir simulator. We're also going to use CMG, but we're going to create our own. And what do we need to do that? Well, the first one is the things you learn in Reservoir 1 and 2, right? What are the conservation equations? And we'll review those here. And the other things you've really known for a long time if you took 310, right? The MATLAB class, if you will. So these are things like root finding and solving equations and interpolation and all this stuff, right? So how many of you are experts at MATLAB? No one? Not a single expert? So I think Dr. Balhoff visited you guys that maybe if you took Reservoir 2 last semester at the end of the semester and made you aware of a bunch of videos that he made and told you to watch them over the summer, right? Because you're going to need them for this class. Who watched those videos? No one? Okay.
Where can we find them?
We'll talk about that later. I'll show you here in a minute, right? So, if you're not a proficient at MATLAB, you get about 2 weeks to spin up because that's when your first homework is due. And your first homework, turns out, is all stuff that you should know how to do from 310. I mean, you could work it today if you have a little bit of computing skill, right? We'll talk about where you can watch the videos and brush up and other things. And so we'll skip this one. So you might have a question, well, why can't we just spend the whole class, the chances of me writing a reservoir simulator or using a reservoir simulator in my job are close to zero. Therefore, why do I need to waste my time? Why can't we just learn to be experts at CMG or Eclipse or some other commercial simulator? And so here's some reasons. There's great danger in using software that you don't know. We have an expression. I've been doing computational mechanics for about 15 years now, in different forms, different physics involved. We have an expression that's garbage in, garbage out, right? You don't want to be a garbage in, garbage out analyst. And I even have graduate students come to me sometimes and just show me results that are clearly wrong. Clearly wrong. And I know they are because I have intuition, or I sort of have done enough computation in my life that I know that that can't be the answer. Sometimes it's as simple as they don't follow trends that, as you increase injection, the pressure doesn't increase in a closed, something really off, right? Something really odd. And so, if you have some understanding of physics, that can help you have some intuition, you know what the code should be doing, that can help you have more confidence in your results. And we'll also talk about other things besides just intuition that can help you have confidence in your results. Like, I mentioned earlier, things like convergent studies and other things like that can help. And we'll talk about some of that in that class. Also, like when I go back to that very first or third slide or whatever, I said the hardest part of the problem, or the thing that distinguishes us as engineers, are deciding how to go from the real problem, right? The real problem being, every characteristic volume that's 20 angstrom by 20 angstrom is different from the one next to it, right? And it's a long ways from 20 angstroms to 2 kilometers where we're doing these simulations, right? So, the hardest part of this process is making the correct assumptions, taking the real problem and developing a mathematical model. And when you have a simulator, someone else has done that for you. And you need to know a little bit about what's in there so that you can decide for yourself, is this reasonable, right? I mean, are these assumptions reasonable for the problem I'm about to solve? And so that's a good reason to know kind of what's in there. And, the other point, knowing the mathematics makes you an engineer and not a technician, right? I mean, you can be, particularly I'm thinking, when it comes to software, there's lots of people with just high school diplomas or associate's degrees that are really smart people, and they're excellent. They become excellent at using a computer to do things like computer-aided design and drafting and other things like that. But what separates those guys from the engineer is that the engineer also has, can also do all of that stuff, but also has an understanding of the math and physics, and can take that computer-aided design, which is essentially just a picture, and turn it into some mathematical model that we can then impose some assumptions on computer solution and make economic decisions based on them. And the last point, especially you guys are seniors, right? I mean, $38 oil, you might be thinking about graduate school. If you go to graduate school, there's a good chance that you might be writing your own reservoir simulator, because now you're going to be adding physics. You're going to be pushing the edge of what's known. You're going to be adding physics to these simulators. And so it might be you. It might be you as soon as next year. Or you might go to work for a company like CMG, and you might spend your whole career developing and improving reservoir simulators. Somebody has to, right? They're not written by computer scientists. I used to work at San Diego Government Research Lab, and it's known for supercomputing. And there was a big movement, sort of maybe in the 90s and where late 90s, early 2000s, where sort of the idea was, well, we're just going to, the engineers can focus on developing the models, and they can have their own research codes, and sort of once they figure out and they know it works, then they're just going to hand it to a computer scientist, and this computer scientist is going to take that and know exactly how to make it parallel to run on 1,000 processors and get the solution in the fastest amount of time. And that whole idea failed miserably, because a lot of times, when you're designing algorithms and other things, it helps to know and understand the physics, and vice versa. If you know and understand the physics, sometimes you can think about an algorithm to, a little easier to get to a solution faster. And so, now at places like Sandia, which are still known for supercomputing, all the national labs, it's engineers that are writing the fastest, best computers in the codes in the world, and at CMG and other companies like that, it's engineers that are really writing the bulk of these codes. So that could be you. Somebody has to do it. There's just kind of a picture of a reservoir from CMG, and we talked a little bit earlier. I had you guys name some Um, some simulators and so there's just a list of ones you might know. The CMG and Eclipse are by far, I guess, the two most common, but there are many others, and including several that have come right here from UT. So UT Chem's been developed for like 30 years right here, and IPARS is a code developed out of Mary Wheeler's lab, and GPass is Kami Stefanori's lab. And Tough2 is a open source code from Lawrence Berkeley National Lab.